in this review, we study 4 concepts. So we're going to study about the first one is geometric series, and then we also gonna talk about the telescoping series, and then we can talk about the harmonic series, and then finally we will talk about the integral test. As a consequence, we can talk about the P series. So let's start with the first one. So the first one is about the geometric series. So what's a geometric series? So if you can write a series in this form, so you start with a number and then you every time you multiply by a constant. So the constant is what we call r. So we may multiply by r every time. So the second term would be ar in this case. So it is an a r squared, like that. So that means you can write the nth term as an or an minus 1, depending on how you want to write it. But if you write it like that, your n start with 0. If you want to write n minus, so that's another way to write this one. So sometimes some people would like to write this as a r n minus 1. So it's up to you, but make sure that you start with the right notation. So let's go with like this. But then this is not the nth term, this is n plus first term. But that doesn't matter. So then what's gonna happen? So this one is called a geometric series. So is a geometric series that converges when the absolute value of r less than 1. Okay, it's going to converges when absolute value r less than 1. So we can write the sum like this. So this is going to convert to sigma. So in this case we can start with 0 to infinity, because that's how we write it. So it's a r n. You can see that when n equals 0 you get a. So this can convert to a, the first term, whatever the first term, divided by 1 minus r. So this happens when the absolute value r less than 1. And then if the absolute value r is greater than or equal to 1, absolute r greater than or equal to 1, the series diverges. So that is what we normally call the geometric series test. So when the absolute r less than 1 is going to converge, absolute value r greater than or equal to 1 is diverge. So we remember it's like that. So this is 0. So we have 1 and negative 1. So what's going to happen? Inside the open interval, negative 1 to 1 is going to converge. That's where it's going to converge. So outside it's going to diverge. Okay, so let's look at some examples. So let's do 2 examples. So the first one is sigma. We can have like n going from 1 to infinity, 9 times 2 to the n minus 1 over 3, let's say 5 to the n, something like that. So we have a series which is 9 times 2 to the n minus 1 divided by 5 to the n. So if you get something like that, so what we need to do is we need to find the r. So that's one thing, we need to find the r. So so how we can do that? So so we're gonna take the constant term out. So what we're gonna do, we're gonna have a common index. That's what we need. So actually this is not actually I want, so I'm gonna kind of slightly change the number, so there's an extra in there. So let's change it to 2 to the n minus 1. So this is a little bit easier, but we can do the previous one also, but that's a good problem if you want to try it. But let's do this one. So what we can do, we need a common index. So what we can do is, you can see that there's a 2 to the negative 1. So 2 to the negative 1 will be 1/2. So we can write this one as, you can write this one as sigma n going from 1 to infinity. 2 to the negative 1 becomes 1/2, so it's a 9/2. And then we can write this one as 2 to the 5th with the common index n. So the goal is to write with the common index. So it doesn't matter what the index is, just have a common index. So now we have everything we need, and then we know that in this case r equal to 5th. So the absolute value r is 2/5, which is less than 1. So the series converge. So the series converge. Series converge. So good. So now we know that it's going to converge to a over 1 minus r according to theory. So what is a? How to get the a? A means the first term. So how to get the first term? Just plug in the first value of the index. So the first value of the index is 1. So when you plug in 1, so what are you going to get? So you can see that in this case, when you plug in 1, you're going to get 9/5 times 2/5, so 9/5, right? So you're going to get 9/5. So that's the a. 9/5 divided by 1 minus r. R is 2/5. So how to simplify? So you can say 9/5. So here you get 3/5. Once you take the common denominator, common denominator is 5. So you're gonna get 3/5. And this you can write as 9/5 times upside down this. So you're gonna get, so 3 get cancelled, so one of the 3 get cancelled, so you're gonna get 3, so you're gonna get 15/2. So the answer is 15/2. So that's the answer. And then, so let's do another problem. So how about this one? This is the next example. So we can do a sigma, let's say n going from 2 to infinity, 2 to the n plus negative 1 to the n over 3 to the n. You can see that this is not just one term, there are 2 terms. So this is not one geometric series. You need to split this. So what do? You're going to split this into 2 series. That's how we kind of do this kind of problem. So we're going to split this into 2 series. So it is sigma n going from 2 to infinity. We can write 2n over 3n with the common denominator plus sigma n going from 2 to infinity negative 1n over 3n. Now what we're going to do, we're going to kind of find the r in both cases, but what we can do, we can write them using a common r. So you can write this one as common index, so it's a 2/3 to the n, and then here sigma n going from 2 to infinity negative 1/3 to the n. Now we know what's r. So in the first one you can see r equal 2/3, so which is less than 1, so the series converge. And in the other one also r equal negative 1/3, that means the absolute value of r is negative, r is 1/3, which is less than 1, so converges. So both converges. So that means we can use the sum formula here. So sum formula is a over 1 minus r. A. How to get a? You have to plug in the first index value. So first index is 2. So when you plug in 2, so you're gonna get, you have to square this. So you can write this one as 2/3 squared over 1 minus r is 2/3 plus here the other one is again negative 1/3, the same thing, you have to square that again, 1 minus 1/3. So be careful with that. There are two minus sign. And then we can simplify this. How to simplify? The top is 4/9, and the bottom is take the common is 3, so it's 1/3, and then plus 1/9. And then what happened here? Minus minus become plus. So I mean you're gonna add them, so it becomes 4/3. And then you can simplify the two. So we can write this one as 4/9 upside down 3/1 plus 1/9 upside down 3/4. So you're gonna sum it. So you can see 3 get cancelled. You get 4/3 plus the other one is 1/12. Take the common denominator 12. So that means you have to multiply by 4. That means you're gonna get 4 times 4 means 16 plus 1. That means 17 over 12. And you know that you cannot cancel 1 and 1. So it's 17 over 12. So that's the sum of the series. So as an exercise, I'm gonna give you this one for you to try. So what do you to try? So let's make a slight change. Sigma n going from 2 to infinity. So let's say 9 times 2 to the 2n minus 1 over 5n. So what do you think about that? So this needs a little bit of algebra, but you can see it's not that bad. I will tell you that this series converge. Okay, that's the hint. This series converge. So see what you're gonna get. So okay, one more thing. What if one converge, one diverge? So what if one converges and the other diverges? So if one converges and the other diverges, the whole series has to diverge, because the converged one has a finite number, but diverged one either goes to positive infinity, negative infinity, or gonna fluctuate between the two. So what's gonna happen in that case? The whole series diverge. So in this case, the whole series diverge. So it's something you'll remember. When there are two series, if one converge, one diverge, or both diverges, then the whole series has to diverge. So this is one of the results that you wanna remember. Sometimes that's what happens when you try to do it, because for example, if I put instead of 2, if I put 4 here, the whole series is gonna diverge. So that's a good example for you to try. Okay, I can put that also as an exercise. So you can try this one also. Sigma n going from 1 to infinity, let's say 1 to infinity. I just slightly change this one, 4n plus negative 1n over 3n. So now what's going to happen? This can diverge, so that you can ask for a finite sum. Okay, so that's about geometric series. So let's go to telescoping series. So that's the next topic. So the telescoping series, so number 2, telescoping series. Telescoping series. So what's a telescoping series? So let's say you have a series, we write an. What you can do is sometimes you can write an, the nth term, as a difference of two consecutive terms like that. We don't know anything about bn, but you can write as a difference of two consecutive terms. So that's the kind of goal. So you can write this as a difference. So difference of two consecutive terms. So if that is the case, something interesting happen. In this case, we call this kind of series telescoping series. So we call such series telescoping series. Okay, we call such series telescoping series. So so it will be clear if you look at a problem. So let's try to look at the problem. So let's say this example. Find the sum of the series. Find the sum of the series, find the sum of the series. Let's look at this one. This is sigma n going from 1 to infinity, 3 over 4 n squared minus 1. So that's the series. Let's think about this. So right after you see the series, it doesn't look like anything pretty much. So what you do is you're gonna factor the denominators. Let's look at the nth term. So let's look at the nth term. So what's the nth term? So the nth term is 3 over 4n squared minus 1, and you can see that you can factor the bottom. So what are the factors? So the factors are, because 4n squared means 2n whole thing squared minus 1, so this can write this one as 2n minus 1, 2n plus 1. So this is interesting because you can see that, what do you see? These two are two consecutive odd numbers. See that? Consecutive odd numbers, right? Consecutive odd numbers. That means we get something. You see that those are consecutive. So since they are consecutive, we can go with the argument, because you may be able to write this as a difference of 2. So what we're going to do is we're going to use the partial fraction method. So let's use the partial fraction method. So what we're going to do, we're going to assume that 3 over 2n minus 1, 2n plus 1 equal, or actually identical to a, the larger one, plus the smaller one. Smaller one, larger one is as a fraction, it's go backward. Alright. So what we're gonna do now, we're gonna multiply by the common denominator. So we can write this one as 3 equal a. You just use any method you know. So you can use the hiding method or just a substitution. So it's not that bad. So we can say I'm gonna plug in. What you wanna do? You wanna make the term on the right side 0. That means you're gonna plug in n equal 1/2. Once you plug in n equal 1/2, because that makes the parenthesis, the term in the parenthesis 0. So that's how we pick this. So you can say 3 equal 8 times you plug in 1/2. This get 1 plus 1 plus 0. So this is gonna give you a equal 3/2. And then similarly, when you plug in n equal negative 1/2, you get 3 equal, because then the first term gets 0. So 0 plus b, you're gonna get negative 1, negative 1. So this is gonna give you b equal negative 2 3/2. Okay, so we get exactly what we want, because it has to be the same number with opposite sign. That's how it should work. So now what we can do, we can plug in that. So that means you can write your a in like this. So it is 3/2 over 2n minus 1 minus 3/2 over 2n plus 1. You can write this in a kind of nice form. What we normally do is in a fractional, in a partial fraction problem, we're going to bring the 2 down. So we can write this one as 2n minus 1 minus 3 2n plus 1. But we don't need that for this problem. We kind of go with the we're gonna go with this version, because that's much helpful for our problem. So what are you gonna do now? We can write the first few terms. Okay, so like probably we look at the partial sum. We can write the first n terms. So let's write the first n terms. So if you write, so what we're gonna do, we're gonna go to the series, and because we know that each term looks like this now. So this is the format of one term. So each term looks like this. With this n term. So what we can replace all those terms from this. So that means your series now gonna be this. So but we only look at the partial sum. So we're gonna go from n going from 1 to infinity to the nth term. Yeah, it's kind of bad index. We normally use n for that. So k would be much better. It's okay if you understand what you're doing. So it is 4n squared minus 1. Actually, I kind of don't like it. So so let's change it. Can put k here, k there, because, or just change the top to k. So that's another way to do it. So I'm gonna change this to k now, because it doesn't look good. Okay, so because you can have n in both places, so there will be two different indexes, one here, one there. It will be different. You cannot have the same. Okay, it's like integration. So let's write first few terms. So I'm going to start plugging the number 1, but we know that each term have that special format. So if you plug in 1, you're going to get 3 halves minus 1 minus 3 halves over 3. That's the first term, plus the second term. It is 3 halves over 3 minus 3 halves over 5. That's the second term. And then 3 halves over 5 minus 3 halves over 7. We just write just few terms just to see the pattern. So plus dot dot dot. You're going to get 3 halves. When you plug in, you're going to get 2n minus 1 minus 3 halves 2n plus 1. So that's the nth term. Now let's see the magic part. So this is the magic part. So what's going to happen now? You can see this term get cancels with that term, and then this one cancels with that. So the same thing happen. So this cancels with the next one. So you keep going, and then this one get cancelled. So you only get the first and the last. So that means what you end up getting is the first and the last. So that means your sum simply become 3 halves minus 3 halves over 2n plus 1. So that's the partial sum. This is what you get as a partial sum. So now what we can do, take the limit. Okay, so we take the limit. So that means your actual sum of the series in going from 1 to infinity, 3 over 4n squared minus 1 is equals the limit of this sum when n goes to infinity, the limit of this. So it is 3 over 2 minus 3 halves 2n plus 1. But we know that when n goes to infinity, this term goes to 0. So you simply end up getting the first term, so 3 halves, and which is finite. So it's finite. So that's where the series converge to. So you can see that this is a really nice problem. So you can try some other problems. So I can give you a couple of problems for you to try. So how about this? So you can try, let's say, sigma n going from 2 to infinity, 3 over n plus 1 n plus 2. You can see that this is already factored nicely. Sometimes that can be help. And how about this one? Another one, sigma n going from 1 to infinity, 5 over let's say we can write this one as n squared minus 4n n squared minus 4n plus 3. Yeah, you can try these two, see how things are going on. Good. So let's go to the next topic. So let's go to the harmonic series. That's the next one. So number 3, the harmonic series. Series. So this is one of the very important example in series studies, because we use this a lot. Because this is like really good, provide very good count examples. So what the series looks like. So the series is sigma n going from 1 to infinity, 1 over n. So let's look at the terms: 1 plus, 1 half, 1/3, 1/4, like that. But we know that the harmonic series diverges. Okay, so that's one result. So if you look at the sum, this actually goes to infinity. So as a sum, you can say this is infinity. So we don't write it like that. When you write it like, you can say as n goes to infinity. So you can see it like that as n goes to infinity. Oh, otherwise you have to say equal. So that's a two different notation. Okay, but when you write the arrow, you have to say as n goes to infinity. Okay, because this is just one thing. Good. So one important thing is this provides good counter examples. So this is one very good one. So for example, you know that if you say like this situation, if you say a n equal 1 over n, this goes to 0, but the corresponding series a n, this is sigma 1 over n, thus diverges. So this is one situation where the corresponding sequence converge, the series diverge. See that? So yeah, so the sequence converge, the corresponding series diverge. Okay, so that can happen. So this is one good example. Good. So let's remember this like this again, writing I'm gonna say a good example. For a series sequence converge and the series diverge. Okay, so yeah, I'm writing several times because it's that important. Good. So let's do one example from this one. We don't need many. So how about this one? So let's look at this series, n going from 1 to infinity, 1 over n plus 3. This may not look like the harmonic series because it doesn't start with that. Yeah, so this is almost look like harmonic series. So we're going to say almost like the harmonic series. Since we can write this as, how we can write this? So we can write this one as sigma n going from, we can say 4 to infinity, 1 over n. So this is the same thing. You see that? When you write sigma n going from 4 to 1 over 4, then you're gonna get the exact same thing, because when you plug n equal 1, you get the previous one. So that means, so this harmonic, but it's not exactly the harmonic series because we missed the first 3 terms. So so they kind of a close resemblance, but it's not exactly the same. And then how to prove that this series converge? It doesn't converge, diverge, but you can see. So if you really want to show that that's gonna diverge, we can use the same argument, or we can use what we call, so later we're gonna use one of the important tests called the so we're gonna consider this problem again in, so consider again in the limit comparison test. Okay, because this is the easiest way to show that. Just use the limit comparison test, because when you look at the limit is 1. So limit 1 means they behave the same, but one diverge, so the other one has to diverge. Yeah, so we're gonna come back to this problem later. Okay, so let's go to the last part of this discussion. So that is the integral test. So number 4, the integral test. Integral test. So integral test. So what's the integral test? It is sigma an. So you have a series, and what's going to happen is your n term is given by a function. So when you plug in n equal 1, you get the first term, n equal 2, you get the second term, like that. And this function has 3 properties. Function has 3 properties. So what are 3 properties? All 3 are important. It has to be positive, and then it has to be continuous, and it has to be decreasing. Okay, so it will be a decreasing function. So if those three satisfies, then what's going to happen? Sigma an converges if and only if the series 1 to infinity, I mean you can pick any number you like, 1 to infinity fx dx converges. So when you say if and only if, that means if it converge, the other one converge. If it diverge, the other one diverge. That's what if and only if means. Okay, so if it converge if and only if, converge means diverge if and only diverge. So we don't write both. So if and only if means that. So we're gonna both the same. So behave the same way. Okay, so behave the same way. So that's easy to remember. Okay, so if the integral converge, the series converge. If the integral diverge, series diverge. Okay, so let's look at one nice example. So how about this one? So we can use this technique when the, okay, let's write it. So that's a good one to remember. So we can use this technique. Use this method when the function f is easy to integrate. So that's when we try to use it. It's easy to integrate. If the function is easy to integrate, we can use this technique. Okay, but sometimes it depends. There are some other techniques that's much faster, but there are some problems you really need to do this. So it depends. Yeah. So let's look at this problem. Sigma n going from 1 to infinity, n over n squared plus 1. So if you get this kind of problem, so you can see that this is kind of, if you look at the corresponding function, it is fx equal x over x squared plus 1. This is very easy to integrate using substitution or for formulas. So that's what we do. So we're gonna go with the function. So it's easy to integrate. So fx equal x over x squared plus 1. Remember, we have to show those three properties, but we know that when n goes to infinity, when for large x, this is almost looks like, this is what we call asymptotic. It looks like, okay, this we use the tilde notation. Tilde means like this for large. Okay, so it almost looks like 1 over x. Why 1 over x? Look at the dominating terms. This is x, this is x squared. If you just those two and simplify, x over x squared means 1 over x. That's where that term coming from. Okay, x over x squared means is 1 over x. So you can see that so it almost looks like it's what we call asymptotic to 1 over x as x goes to infinity, or for large x. But now we consider the properties of 1 over x, because we can ignore first few terms of a series, so we don't worry about what can happen at the beginning. So but this series 1 over x is so we can say it is, we now only worry about 1 over x. Okay, so it is positive, continuous, and positive, continuous, and decreasing for any x greater than or equal to 1. So that function. Okay, so we can look at 1 over x, but it's the discontinuity is at 0. So but we don't worry about 0, because you can always consider larger values. Okay, so but you need to at least mention that. So it's satisfy all three properties. That means we can use the integral test here. So let's try to finish the problem now. So what we're going to do, we're going to consider the integral x over x squared plus 1 dx. So this is an improper integral, so you need the limit definition. So it is b goes to infinity 1 to b x over x squared plus 1. This is very easy to integrate. So what we normally do is we're gonna get the 1/2 out. We're gonna put 2 in, because that's the derivative of the bottom function. That means dx, actually forget the dx. So this is easy to integrate. So it's a limit, it's a log. So b goes to infinity 1/2. So this is simply natural log x squared plus 1. We can do the parenthesis here. We don't need the absolute sign because it's always positive. So this is evaluated at b equal 1, 0 and 1. So you can see limit b goes to infinity. So what do you get? 1/2 ln b squared plus 1 minus 1/2 ln 2. We need the parenthesis because of the limit, but this is infinity. So diverge. So we need to write it, okay? Diverge. So let's finish the argument. So by the integral test series sigma, it's a good idea to write the whole thing here, like just to make it complete. Series diverges. Okay, so it's not that bad, you know. So you can integrate this, and so this is kind of complete argument for this kind of problem. So I'm going to give you one problem for you to try. So how about this one? So you can try this one. So this is an exercise. So see what you can say about this one. Okay, I'm going to give 1 over n natural log n square root. Okay, like that. But can we start with 1? If we start with 1, we know that log 1 is 0, so we don't start with 1, we start with 2. So 2 to infinity. Okay, so test. What can you say about this one? Okay, good. So that's about that. So one of the major consequences of the integral test is the what we call the p integral. So let's talk about that, because this is one of the important one. P integral. What's the not the p integral, actually p series. Yeah, p series. So we have the p series. So let's talk about that. So p series. So what's the p series? Sigma n going from 1 to infinity is very equal to similar to that. So it's n to the p. That's what we call the p series. In the integral we have 1 over x to the p. So the result is exactly the same. This one gonna converge if p greater than 1, diverges if p less than or equal to 1. And then why this is related to the integral test? Because we use the integral test to prove this. So and then what we notice is the same thing. So you can see we have 0 here, 1 and -1. Actually that's not related to this one. So we only need 1 here. So what this says that, I'm going to draw this. So what this says that, so you have a 1 here. So it's going to converge on this side. So open interval, it's going to converge on this side. Okay, so it's going to converge here, diverge everywhere else. Okay, this side is diverge. So this is, so 1 to infinity converge, -infinity to -1 close, diverge. Okay, so yeah, so this is what we call the p series test. And then you can see one of the good example of this one is the harmonic series. So when p equal 1, you're gonna get sigma n going from 1 to infinity. This is 1 over n now, because 1 over 1. So you get 1 plus 1/2, 1/3, 1/4. So this is one such example. That is when p equal 1. But we know that when p equal 1, the series diverge. So this is another way to say it. So this is what we normally call the harmonic series. So harmonic series diverges because of p series test also. Okay, let's try to do 2 quick examples. How about this one? Let's say so the first one, sigma n going from 1 to infinity, 7 over, let's say, n to third. I mean, you can ignore 7 here. 7 is a number. Or what you can do, you can pull the 7 out and kind of make it clear like this. So you can do that also. So now it's like kind of clear. Pull the 7 out. So you can see that this is a p series. P series with P equal 2/3, which is less than 1. So the series diverges. So that's the easiest way to do this. So let's do one more. How about this one? Sigma n going from 1 to infinity, n squared minus 3 over n to the 5/2. So if we get something like that, the best thing would be to split this. So we can split this into two series. So sigma n going from 1 to infinity, n squared over n 5/2 minus sigma n going from 1 to infinity, 3 over n 5/2. So if you simplify this, you're going to get sigma n going from 1 to infinity, 1 over n half minus sigma n going from 1 to infinity. Just rewrite this one, and you can see here P equal 1/2. So absolute value is less than 1. So the series diverges. So if one diverges, so it's this one diverges. But what about the other one? So if you look at the other one, for this one, P equal 5/2, which is greater than 1, so converge. So if one diverge, the other one converge, the whole series diverges. Okay, so because of this, so one converge, one diverge. If both diverge, we don't know, it can be anything. If both converge, they converge. Both diverge, anything can happen. If one diverge, one converge, the whole series diverge. So therefore sigma, you can say n going from 1 to infinity, n squared minus 3 over n 5/2 diverges. Okay, because one converge, one diverge, so the difference has to diverge, because the converge one has a finite answer. Okay, so this is the kind of things about those four series related topics. Thank you.